Hello and welcome to today's lecture on Pier Luigi Nervi and the Italian tradition of rib vaults. We're recording today from Rome, where we're standing inside of one of Nervi's greatest designs, the Little Sports Palace. You'll see behind me the beautiful designs of all the patterns, and we're going to, in part of this lecture today, go over how he designed and built this structure. Later today also, we're going to be joined by my colleague, Tullia Iori, who's a professor at the University of Roma Tor Vergata, and she's an expert on Nervi, and she's an expert about this little sports palace, and she will discuss it with us as well. The objectives for today's lecture is to describe Nervi's aesthetic and its connection to his Italian heritage. Also to define the construction methods developed by Nervi that made his shells feasible and economical. And we'll also look at some of his significant structures, for example, the Florence Municipal Stadium, the Turin Exhibition Hall, Gatti Wool Factory, Little Sports Palace, Large Sports Palace, and the Flaminio Stadium. Just like we've been doing throughout this course, we're going to look at the three-part perspective, the scientific, social, and symbolic perspective of Pier Luigi Nervi. From the symbolic perspective, we're looking at the imitation. In this case, it's not imitation of another designer, but the imitation of an art historical tradition of rib patterns that we see throughout Italy. From the social perspective, we see innovations in construction, in particular two innovations, ferro-cement and prefabrication. And from the scientific point of view, we have inspiration. We have these great designs that Nervi created through efficient ribbed forms. Starting from the symbolic, if you tour Rome and you tour Italy, what you're going to see are ribbed dome patterns. So starting, for example, from the Pantheon, we see this coffered pattern in this dome, and the Pantheon is the largest dome made out of concrete without reinforcement. Also in the Vatican Museum, we see these patterns of ribs in several places. As you walk around the Vatican Museum, you'll see these domes with rib patterns. And in the Roman Forum even, you'll see this ribbed pattern there as well. So in several places along Rome, you can find these rib patterns. You could go to Turin and find it in San Lorenzo as well. Nervi never wrote about this inspiration that he had about this rib pattern throughout Italy, but it's something that David Billington observed and speculated that it did influence Nervi, and it's something that I agree with him as well. What you see on this image is a collage of Nervi's designs where you see the rib patterns throughout all of them. And these are designs that we are going to cover in today's lecture. When I was learning about Nervi, David Billington would tell me that what is important about him is that he is first a builder. He knew very well the conditions in Italy, and therefore his designs were competitive. Nervi's emphasis when approaching the designs for vaulted structures was different from the Germans that we studied last time. Specifically, Dischinger and Finsterwalder studied the mathematics, and they focused on the mathematics, and Nervi's focus was a little different. In The Tower and the Bridge, quoting David Billington, he says, "During the 1930s, Nervi was designing and building large concrete structures, mostly as a result of winning cost competitions, although his intellectual bent was for reflection and aesthetics. Whereas Dischinger and Finsterwalder were writing about domes and barrels designed on the basis of the mathematic theories they had developed, Nervi was writing such articles as The Art and Technique of Building, Thoughts on Engineering, Problems of Architectural Achievement, and Technology and the New Aesthetic Direction. He wrote no treatises on scientific analysis." Nervi began practicing after graduation from Bologna in civil engineering in 1913. After graduation, he worked for Società Anonima per Costruzione Cementizie, and in 1923, he left the company to work for himself, and he founded his own company, Nervi and Nebbiosi. I'm going to quote once again from The Tower and the Bridge, where David Billington explains the transition that he makes as he goes to work on his own. He writes, quote, "It was not until 1932, at the age of 41, that he completed a major structure on his own." And he's referring here to the Florence Municipal Stadium that we'll look at next. David continues, "During those nearly 20 years of practice, however, he gained design and field experience with reinforced concrete, so that when he first began to design and build his own works, they were the product of considerable maturity." In this same year, 1932, Nervi breaks from his partner Nebbiosi and forms a small family-run company with his cousin and calls his company Nervi and Bartoli. Let's look at this municipal stadium in Florence that essentially launches Nervi's name. It was completed, as we stated, in 1932, and it is a horizontal cantilever. At this time, reinforced concrete was still a relatively new construction material. With this project, Nervi demonstrated its potential as a strong material, capable of great spans with relatively little thickness, and also a material capable of great aesthetic expression. There were two main features to this municipal stadium: the stadium itself, meaning the horizontal cantilever, and also the spiral-shaped beam supporting the staircase, which has another spiral-shaped beam intersecting it to prevent twisting. By leaving the concrete naked or exposed and designing with a clear articulation of how the forces are carried in the structure, he illustrated for us the art of the engineer. My colleagues at Princeton, Sigrid Adriansens and David Billington, performed a structural analysis of this municipal stadium, and it's published in the Journal of International Association for Shell and Spatial Structures in 2013, which dedicated a special volume to Nervi and his works. And in that analysis, they show that the resultant of the gravity forces, meaning if you were to concentrate all the gravity forces into one location, the location of that force resultant is located where you see that arrow pointing down. And that arrow shows that it falls in between the foundations, point D and E. Because it falls in between points D and E, the foundations are not in tension. If it fell to the left side of point D, for example, point E would have an uplift force, and the foundation would need to be designed for tension, which could be very expensive. So we see economy here, not only in the structure itself, but in the foundations as well. I have said and shown in the many lectures I give on structural art and structural artists how the greatest engineers produce some of the best works under constraints. These constraints are economical constraints, or they could be spatial constraints, meaning under tight spaces, and it could be a constraint of material deficit. And this is what we see with Nervi. He's designing under the constraint of economy as well as material. Soon after the completion of the stadium, what happens is that Italy shifts to a state of autarky, or economic self-sufficiency. Since metal reinforcement is primarily imported, reinforced concrete structures become an anti-autarkic material. Steel reinforcement was partially banned in 1936 and then fully banned in 1939. But cement was being produced in mass quantities in Italy, so engineers experimented with other means of reinforcing concrete, such as bamboo or aluminum. Now we move to the social aspect, the innovations that Nervi made in construction, in particular ferrocement and prefabrication. The innovation in construction is referred to as the Nervi system, a terminology given by my colleague Tulia Iori. And it refers to, one, a construction practice, which is structural prefabrication, and second, a material, which is ferrocement. The first opportunity that Nervi had to reinvent his construction methods was for a project for the Aeronautic Division, in other words, the Air Force in Italy, who needed hangars to protect its planes and were exempt from the steel reinforcement ban. What we see is a series of aircraft hangars that were built. The first series were built between 1935 and 1938, and in this series, ordinary cast-in-place reinforced concrete was used. In the second series, from 1939 to 1942, Nervi is using his innovation of structural prefabrication. Nervi compares the economy of these two types of hangars, the first and second series, and he writes that the prefabricated series saved about 30% in steel, 35% in concrete, and 60% in wood. These airplane hangars were on the order of 100 meters by 40 meters, and they were made again by prefabricated concrete elements. And many such hangars were built for the Italian Air Force that were unfortunately later destroyed by the retreating Germans. So what is structural prefabrication? In structural prefabrication, the concrete is cast in a reusable mold or form. The image shows how we have wooden formwork on top of which the concrete is cast, and then when the concrete hardens, the wood mold is removed and then reused again for another set. Since the pattern of this dome is repeatable trusses, he uses the same wood formwork over and over again, thus saving all that wood, and hence the 60% savings that he mentioned earlier. The prefabricated segments have protruding from them steel reinforcement, so that when the joint comes together, where 4 trusses come together, we have a joint that is connected by welding those bars together, and then concrete is cast in that joint. Examining the joints after the Germans collapsed the structure, it was noted that they fared better than the single elements themselves. The image shows one of those prefabricated hangars. In the background, the cast and placed hangars completed earlier. And in the foreground, we see the prefabricated segments, the truss segments, that are going to be used for another hangar that is going to be built nearby. His structures were very difficult to calculate statically, and so he did some analyses using scaled models with the assistance from a professor at Milan Polytechnic. He used these scales models to study the behavior of the structure and have more confidence that they were structurally sound. We have explained one of Nervi's innovations, structural prefabrication. Next, we look at his second innovation, ferrocement, whereby combining these 2 innovations, Nervi becomes known as being one of the greatest structural artists in history.